All right, thanks. So similar to the last two talks, I'm in a setting where I want to use lightweight threads, so something like what's provided by Domainslib, for concurrent or interactive applications. So one place where you might want to do this, I didn't coordinate the motivating example with Vesa, but we ended up in similar places, but with a slight twist. So let's say you're building a small web server. I want to have one big loop that accepts connections. And then let's say I want to handle each client in a separate thread. So whenever I accept a new connection, I spawn a new thread to handle that connection. And that takes in those requests and then gets garbage collected when the connection is closed. The twist is in the background, I want to do some analytics. And maybe what I want to do is I want to check the request log and maintain a list of hosts that are bad. Maybe they're performing too many requests, and I think they're trying to perform a denial of service attack or something. So I have another loop that runs in the background and trawls over the request log and tries to classify these hosts. So maybe it also wants to do this in parallel. Remember, I have a lot of threads I can use. So it takes the request log in parallel, spawns a bunch of threads that do this computation, and then report back. So there is shared state here. So for one thing, the connection threads place the request in this buffer, which is then handled by the classification loop. And then once the classification loop classifies hosts into good or bad, it stores that in a big hash table that obviously needs to be read by the accept loop so that we can actually ban the hosts that are classified as bad. So one thing that comes up immediately if you try to program this is that I've been saying we have these threads in the foreground and we have these threads in the background. But these fine-grained computation libraries like Domainslib, fine-grained parallelism libraries, don't really have a notion of priority on these lightweight threads. And that's really something that becomes vital here. So in particular, let's say we have 3 priorities and we want to prioritize handling existing connections over accepting new connections. So we'll handle existing connections at the highest priority, we'll accept new connections at a medium priority, and then do the classification work kind of in spare cycles at your lowest priority. So with that motivation, I've built an extension of Domainslib called Priodomainslib, which extends Domainslib with these priorities on tasks. So this is following up on work that's been done in a parallel variant of standard ML and also by some collaborators in Silk. So now bringing this to OCaml. So what needs to change to add priorities? Well, obviously the thread interface needs to change because when you spawn a thread, async a computation, you want to be able to specify the priority. The scheduler needs to change because the scheduler needs to respect priorities. We also want to have mutexes. We have global shared state. We need to protect that. And it turns out we need a new mutex implementation that also respects priorities. So I also have some design goals. One is that it should be a conservative extension of Domainslib. I want existing code in Domainslib to just work in Priodomainslib at one priority. So if you don't specify anything with priorities, we'll assume that you're just running your computation all at one priority, and it should just compile and work. So it should be compatible. The other thing is that I want it to support an arbitrary number of programmer-defined priorities, as opposed to, say, the POSIX priorities, which is specify a number between 0 and 100, what the semantics of priority 42 is, as opposed to priority 85. Good luck. That's up to you to figure out and remember, and also coordinate with everybody whose modules you may be linking with. So we'd rather have them be programmer defined, and you sort of define the number you need and assign them your semantics. The reason that we need a new mutex implementation is that once you have mutexes and priorities, you can have the problem of priority inversion. I'll go over that a bit later in the talk. Speaking of what I'm going to do in the talk, so I'm going to briefly go over the API, motivating it using examples from this web server example. I'll talk briefly about the design of the scheduler. I didn't design a new scheduler for this, mostly using an existing one, but I'll talk about some of the challenges in implementing it in OCaml. And then just the status and yeah, talking about the challenges that I've run into and possibly how to solve them. So we need an interface for priorities. So the priority module defines a new type of priority. So priorities at the moment are totally ordered, but you define them as you need them. So there's this function new priority, which creates a new priority. And so every time you call this, you get a priority that's higher than all of the existing ones. So you define your priorities from bottom priority to top priority. And you can also get the count of how many you've defined and get the top priority and the bottom priority and so on. And there's also functions that I haven't shown for comparing the ordering of priorities. So priorities here are first class values in the system. So in our web server example, we have 3 priorities. The lowest one is this priority that we use to classify the hosts in the background. The middle priority is the one that we use for this loop that accepts new connections. And the highest priority is for serving existing connections. So each of those is just a call to new priority. Here is the updated task API. So if you're familiar with Domainslib, the top 4 functions or definitions will look quite similar, with the exception that async now has an optional priority argument. So the use of this as an optional argument means that we're compatible with Domainslib. When you async a new thread, you can specify the priority, or optionally, if you don't specify it, it's assumed to just async at the current priority. And if you haven't defined any new priorities, that priority is just the single priority that exists in your system. So we're still compatible with Domainslib code. 3 of these functions will be familiar. A new one is that a thread can change its priority. That one, the priority is not optional. You can also, 2 of these 4, sorry, are familiar from Domainslib. You can get your current priority. The await, which takes a promise and waits on it, is totally unchanged. So the way you await on an async thread, you just do that exactly the same way. At the risk of creating yet another incompatible asynchronous I/O library, we also want non-blocking I/O functions. Ideally, this would be integrated with Picos at some point, but I just learned about that 20 minutes ago. So at the moment, that's built into the library. So the way this is used in the web server. It's just a snippet of code. We've accepted a new connection. We want to atomically increment the number of connections we have, add it to the list of some connections that needs to be cleaned up at the end. And then we want to asynchronously spawn a new thread to serve that connection. So we'll do that by spawning a new thread at priority serve B. So otherwise, this looks very much like code you could write in Domainslib, just with that optional priority argument. And then we go back around and continue accepting more connections in the accept loop. OK, so as promised, I need to talk about mutexes. So we have 2 kinds of global state in this web server example. We want to protect it with mutexes. We have priorities. What goes wrong? So very briefly to introduce the priority inversion problem, let's say that you have a low priority thread that tries to acquire a lock and succeeds in acquiring it. And now suddenly a high priority thread comes along and attempts to acquire the same lock. The lock is held, so the high priority thread goes to sleep. So we could already call this a priority inversion, because there is a high priority thread that's doing something very important, but it's blocked on a low priority thread that's doing something presumably less important. This is what's called a bounded priority inversion, and it's generally not considered to be as much of a problem, because hopefully quickly, if the code is well designed, the low priority thread will get through its critical section, release the lock, and the high priority thread can go on its way. The problem with this is that it can quickly become an unbounded priority inversion if we simply, after the low priority thread acquires the lock and the high priority thread attempts to acquire the lock unsuccessfully, let's say a medium priority thread comes along that runs, let's say, forever, and blocks the low priority thread from running its critical section and releasing the lock, which means that the high priority thread is really now sleeping on both this low priority thread and this long-running medium priority thread. So this is really where priority inversions become a problem. So there are a number of dynamic protocols for dealing with these priority inversions. The one that I implement in Priodomainslib is called the Priority Protection Protocol. So it's very similar to a related protocol called priority ceiling, where each mutex is assigned a priority ceiling, which is the ceiling, the highest priority at which this mutex may be acquired. So going back to our example, the low priority thread tries to acquire the lock, acquires the lock. The lock now is green. It's specified with this high priority because the high priority thread also tries to acquire the lock. Now, with the priority protection protocol, when the low priority thread acquires a lock, it actually becomes a high priority thread. So it is immediately promoted to the priority ceiling of that lock. So it proceeds through its critical section as a high priority thread, which means it has precedence over the medium priority thread, and it unlocks the mutex, which can then be acquired by the high priority thread. So we don't have this priority inversion. Just to show how this works in the web server, we have these two pieces of global mutable state. We have the request buffer, and we have this hash table of bad hosts. So we have two mutexes to protect each of those. And they have two different priority ceilings. So the priority ceiling, just like with async, we have an optional argument that specifies the highest priority or the priority ceiling. If it's not specified, the priority ceiling just defaults to the highest priority that exists in the system. So the request mute protects access to the request buffer. Now this is only ever accessed by the classification threads, which are low priority, and the serving threads, which are at the highest priority. So this priority ceiling needs to be at the highest priority. On the other hand, the bad mute, which protects this bad hosts hash table, is not touched by the threads that serve connections. It's only touched by the thread that it accepts new connections, which is at this medium priority, and by the low priority background threads. So we can specify a more conservative priority ceiling for this. We can say that it's not acquired by the high priority threads, only by the low and medium. And so threads acquiring this lock at a low priority are just promoted temporarily to medium. So when we lock and unlock this mutex, basically we don't need to change what we do. So the priority stuff only comes in when we create the mutexes. We need to specify the priority ceiling. I want to talk briefly about the scheduler design. So for more details, see this paper, which gives the details of the prompt isilk scheduler, which is what I've implemented. I'm just going to go through very briefly how the scheduler works and how it's different from the standard Domainslib work stealing scheduler. So as with standard work stealing schedulers for lightweight threads, like the existing scheduler in Domainslib, each worker has a concurrent work stealing double-ended queue. So we just use the work stealing queue implementation from Saturn, which Domainslib also uses. I see the next talk is on Saturn, so I won't say too much about that. In Priodomainslib and in prompt isilk, we no longer have one of these per worker. We actually now have one per worker per priority. So as with standard work stealing, when you decide you're working at a particular priority, I'm not going to go into too much detail on how you decide which priority you're going to do work at, but intuitively you want to work at the highest priority that you can. So see the paper for exactly how that's, at least the heuristic for how that's approximated. So you pop a task off the queue for the priority that you're working at. Each worker does this concurrently. When a worker finds that that deck is empty, so it is unable to find new work locally in its own queue for the priority at which it's attempting to do work, which is maybe the highest priority, it becomes a thief and it tries to steal work from another worker. Unlike in traditional work stealing algorithms, which then do this randomly, randomly choose a deck from another processor to try and steal work from, prompt isilk actually maintains a queue of decks again, a queue of decks at each priority. So instead, we'll go to the high priority stealing queue. We'll take the first deck off of that queue, steal from it, or indeed, under some circumstances, if we're able to, we might actually just take that entire deck as our own if somebody else isn't currently using it. I don't want to go into the details on that. But at least we will steal from that and then push it back on the back of the queue. So in this way, rather than randomly steal, we kind of round robin who we steal from. And that reintroduces a lot of the nice aging heuristics that you get from randomized work stealing, but that would otherwise not actually hold if you just naively do kind of one randomized work stealing instance at each priority. All right, that's all I have time to say about the scheduler. So I want to talk briefly about the implementation status. So I've implemented this as a fork of Domainslib. I've implemented a few small micro benchmarks just for testing pieces of the code, and I've also implemented this web server benchmark, tiny web server, about 300 lines of code. Haven't really done a lot of quantitative evaluation of Priodomainslib yet, so that's still work to be done. There was one experiment that the reviewers very reasonably requested, so that I wanted to just at least give some very preliminary numbers for. So I just got these numbers quickly before getting on the plane. So this is still a preliminary experiment, but the idea is to see if we have just code at one priority, so code that's compatible with, say, existing Domainslib code, and I run it under Priodomainslib, what's the overhead with respect to vanilla Domainslib? So as you can see, there is quite a bit of overhead currently. This is the Fibonacci benchmark from the Domainslib test suite. On 4 processors, Domainslib is getting about 2.5 times speed up. Priodomainslib is getting about 1.75x speed up. So as you can see, there's quite a bit of engineering work left to be done on the scheduler implementation. But at the moment, that's still work in progress. So more fundamental kind of challenges. So long-running sequential threads at a lower priority need to call yield. So ideally, if we have a processor working on a long-running low-priority thread, the scheduler would preempt it periodically to check if there is any higher priority work that it should be doing instead. Unfortunately, this isn't possible in the current Multicore OCaml runtime. And this, I found an issue from November 2016 complaining about this, and there was some discussion, and then it was closed. This would be really nice, but I feel like if KC was asking for this 8 years ago, I don't know what chance I have. The other problem, so the priority protection protocol is kind of nice. That's the one that we implement currently for preventing priority inversions. It would be nice to give some options as to the protocol that's used. For example, a more common one that you hear about a lot is the priority inheritance protocol, where you don't immediately promote threads to the priority ceiling. You do it a little bit more lazily. That would require dynamically changing the priority of another running thread, which requires kind of more explicit handling of thread objects than the current Domainslib implementation does. And I think it would be hard to do that conservatively. I tried a bit. It proved to be pretty difficult. Similar to the kinds of problems you run into with cancellations. So I suspect doing this with Picos might make that a little bit easier as well. So with that, the preliminary implementation is on GitHub, so I invite you to take a look, and I'll take any questions.
Thank you. I'm sure we have questions in the room. I have a question from Gabriel Scherer on remote, who says, it's not clear to me what are the expected benefits of adding priorities to our code due to my lack of experience with this sort of concurrent programs. Certainly throughput is not going to benefit. Maybe it will get slightly worse. I suppose that priorities are designed to reduce latency for some of the computations at the cost of increasing it for others. How do I measure, How do I measure that my priority assignment are achieving the desired result?
Yes, so the measurement problem is interesting. The intuition that I want to kind of give is that you have some threads where throughput is the goal and some threads where latency is the goal. And so, for example, in the web server, for the classification threads, you are willing to give up a whole lot of latency for better throughput. For these foreground interaction threads, maybe you're willing to give up some throughput to get better latency. So the threads just have different requirements. Tuning exactly what priorities you want to give each thread to get the best latency throughput trade-off for each one is complicated. And I've also thought a lot about how to measure this, and measuring it is not easy. Once you have more of a gray area between threads that only care about latency and threads that only care about throughput. But if that's your metric, then it's pretty clear what the right trade-off is. And so you want threads that really care about latency to be high priority. Threads that don't care so much about latency can be lower priority. So I've talked about this in the context of a concurrent interactive program. Even if latency is not the issue, even in purely computational applications, you may still want priorities. So an example is if you're implementing something like A*, some kind of search that's guided by a heuristic, you can, let's say you want to expand a node and you go every direction in parallel. The more promising directions based on your heuristic, you can give those a higher priority. And so then the scheduler would just under the hood, without you doing anything else, prioritize those higher priority neighbors and potentially avoid, find the goal faster, and maybe even if you're searching in an infinite tree, you might actually avoid non-termination by prioritizing the high priority or most promising neighbors.
I would have a question about the mutex modification that you did. So obviously for Domainslib, you had to modify Domainslib to introduce priorities. I'm wondering how many modifications you have to do to PyCos in order to support priorities. So let's say you've got a PyCos application that interfaces through Domainslib, and it uses a mutex that doesn't know about priorities. Can you like assign a default priority to that one and still interoperate correctly with it?
Yeah.
Or do you need to make too many modifications to the interface?
I suspect you would have to. So the mutex implementation really has to know about priorities. And so I suspect if you were trying to combine this with a mutex implementation that is provided by a different scheduler and doesn't know about priorities, I suspect that wouldn't work. So I think you might need either to restrict the set of modules that you can interface with to only those that know about priorities, potentially even actually build in some notion of priorities to PyCos or whatever framework that you're using. I would need to think more about exactly how much modification would be needed, but yeah, definitely some.
Yeah, so currently, PyCos does not have a built-in notion of priority, but it's something that I have thought about. And one way to do it is to actually use the fiber local storage to store a priority for fibers. And then you can have schedulers that will be able to inspect that priority from the fiber local storage. But then you can also have mutexes that also know about the priority and so on. So it should be possible, although, of course, there's limits, like if you have things that don't know about priorities, then they don't care about those, of course.
We should talk.
I have a clarification question. So in order to, when you promote a thread from low priority to high priority when it's for the locking, is it still bound to the ceiling of the mutex? Like, is a low priority thread still able to lock something like after the promotion?
You mean, is it able to lock, once it's promoted to high priority, can it lock something of lower than high? No. So that would be an error. So once it's been, if it's in a critical section of a mutex with a high priority ceiling, it's going to run that at high priority, and then so it then can't try to acquire a mutex whose priority ceiling is medium, for example.
I see. Thank you.
Sure.
Thank you.